So this is a quick refresher on functions. So all of these equations, ordered pairs, and graphs you see are not functions. So when you look at the equations, there's a couple things that they have in common. Number one, we can see that there's a variable in the denominator. When there is a variable in the denominator, it is not a function. Or when the variables x and y are multiplied by each other, it is not a function. So this could still be, if it was 6 equals x, y, or maybe if it was 5x, y equals 2, those would not be functions either. At any point when our x and y are multiplied, not a function. Okay, if we look at the graphs, remember to determine if a graph is a function, we can use the pencil test or the vertical line. So if I draw a vertical line at any point, if the graph hits the line in more than one spot, like this one right here, the line hits the graph twice, it is not a function. Same thing with this one. When I draw a line, the line hits the graph in 2 spots, it is not a function. And let's look at the ordered pairs. When I look at the ordered pairs, I see a couple different things. I see that the variables, the x variable, or the x point repeats 1 and 1, but it has the same y value. So that's so far so good. When I look at the 2's though, the x value repeats with 2, but it has different y variables. To be a function, each x value, remember, can only have one y value. Since 2 has a y variable of 5 and a y variable of 4, that means it is not a function. Each x, remember, can only have one y value. So now on here, all of these equations and graphs are functions. Now we just need to distinguish a function from a linear function. So at the left graph and equations are a function. The equation x squared minus 2x minus 3 is what this graph, or what this equation looks like as a graph. It's a U. If I were to draw a line at any point, as you can see, the line only hits the graph one time. So this is a function. And if you look at the equation, there is no variable in the denominator, and the x and y variables are not multiplied by each other. You do notice that the x value does have an exponent greater than 1. That's okay. That means that it is, and that can be a function. When I look at the linear functions, though, a linear function, like the word in it, creates a straight line. So all of these lines, no matter where it intersects on the x and y axis, is a linear function. Now the equations, if you look at to find the similarities, there are no exponents greater than 1 in the equation. A linear function cannot have an exponent greater than 1, like this right here, in the equation. If you notice this one right here, yes, there's a denominator, but it's a number. It's not a variable. So a number can be in the denominator. Up here, again, even though x and y are on the same side, they're not being multiplied. That's a linear function as well. And y equals x, even though there's no other numbers, that is a straight line. That just means that the line goes through the origin. All right, so now looking at ordered pairs to determine function versus a linear function. So we know in order for it to be function, again, the x variable can only have one y value. So when I look at this set, I have -3, -2, and 0. None of the x's repeat. This is a function. Now to determine if it's a linear function, the easiest way to do that is to first create an x and y table with our points. So I'm going to take the first one, so we have -1 and 0, 2, -3, and 5, -6. So it's definitely a function because none of our x's repeat. In order for it to be a linear function, the ratio, the difference, the y over x has to be the same for each pair. So what I mean, when I look at the first 2 points, the difference in the y's to go from 0 to -3 is a change, a decrease of -3, and to go from -1 to 2 is an increase of 3. So if I were to write y over x, I would get -3 over 3, which gives me -1. If it's a linear function, the next set of ordered pairs would have a constant rate, a slope of -1. So the -3 to -6 is -3. From 2 to 5 is +3. So same ratio, -3 over 3 is -1. So that's increasing or decreasing at a constant rate, which means it's linear. So let's check out the next one, and let's look at the difference. So we have still our x and y. Again, let's find the rate that the points are changing. So to go from 2 to 5, that's an increase of 3. And to go from 4 to 2, that's a decrease of 2. So 3 over -2. I'm just going to go ahead and leave it as 3 over -2. Because remember, by doing this, we're finding really the slope. And slope has a rise over run. So that rate so far is 3 over -2. So let's go ahead. To get from 5 to 11, that's an increase of 6. So we don't want to say no just yet, just because those are different numbers. So to go from 2 to -2 is a -4. Well, let's write this as a ratio, 6 over -4. Even though that's not the same as 3 over 2, 6 over 4 can be simplified. 6 divided by 2 is 3, and -4 to -2. So it still really does have the same constant rate when it's simplified. So this too is a linear function. If these points were plotted, they would create a straight line. All right, let's quickly go through and name it, either function, linear function, or non-function. So this first one, if you think about it, it is going to be non-function. We've got a variable in the denominator. The second one right here, from just looking at it, it looks like it's a linear function because no exponents with my variables, no exponents in the denominator. However, let's get rid of these parentheses. Let's distribute to just get a y equals mx plus b equation. 2x times x. Remember, anytime I multiply something by itself, that's like an exponent. So that actually becomes 2x squared minus 2 times -4 is -8. So this equation is a function, but it's not a linear function. Remember, because x times x is the same as x squared. Right here, y equals 5x plus 4 all divided by -3. This is a linear function. No variables in the denominator, no exponent greater than 1. This one right here, I see that it definitely is a function because none of my x's repeat with a different y, so I need to just figure out the ratios of my x and y to determine if it's linear or not. So when I look at my ratios to get from -6 to -2 is an increase of 4. Here is a decrease of 2. So 4 over -2 is the same as 4 divided by -2 is -2. -2 to +2 is another increase of 4. And here it's a decrease of 2. So same, 4 divided by -2. So this is a linear function. Same ratio. When I look at my next one, to get from 0 to 1, that's an increase of 1 on both sides. So 1 divided by 1 is 1. To go from 1 to 8 is an increase of 7. 1 to 2 is an increase of 1. So 7 over 1 equals 7. That is not a linear function, but it is a function. And then the last one is easy. If I look at it, my x's repeat, but they all have different y values. So this cannot be a function. So now we're going to look at the different scenarios that can match a graph. So what I first need to do is look at the graph. I have my x-axis is talking about time, and my y-axis represents the distance from somebody's house. So basically, as time is increasing, if you go up, you're getting farther away from your house, and if you're coming down, you're going closer to your house. So let's look at A. Mark speeds up as he drives, stops at a red light, slows down, stops again, and then drives home. Well, when I look at this, speeding up, my line right here, if it's straight, that means he would be driving at a constant rate. So he does stop. A straight line would mean he stopped because he's not moving. Time is going, but the distance is not getting farther away. However, it says then he slows down. 3 isn't necessarily meaning he's slowing down. It just means that he's going home, he's getting closer to his home. So A is not correct. So let's look at B. B says Mark drives to his friend's house. So this could be true because if he's driving to his friend's house, he's getting farther away from home. Stays for an hour. So if he's staying for an hour, time is going by, but he's not getting any farther from his house. He drives home at a faster speed. All right, well, 3 would represent driving home because he's going down. He's getting closer to his house, which is down here. Stops for gas, means he's not going anywhere, but time is still happening. And then he continues home. And that would mean at the end, he is home. So B is our correct answer. We can look at C. C says first that Mark drives home. Well, to start out with, he's going up, he's going away from home, so that is definitely out. So for these, you just need to go through answer choice by answer choice to see which matches the graph. So now opposite, we have a scenario and we need to pick the graph. So this one says Jenny is walking upstairs at a steady pace when the school bell rings. At the top of the stairs, she then runs to her classroom. Which graph best represents the scenario? So when I think about this, if she's walking at a steady pace, that means it's constant. That means my line is going to be straight. So when I look at the first and fourth graph, it's trying to trick us because it's making it look like stairs. That is not what walking at a steady pace looks like, that up and down. So that is out. When I look at the first or the middle two, I notice that time is my x-axis and speed is my y-axis. So again, even though both are straight lines, so again, we said if you're walking at a steady pace, it should be a straight line. These two are, but this is where we have to look at what our variables are. The y variable is talking about speed. So if this line right here isn't going up or down, that means that that speed is constant. It is not increasing, it is not decreasing. Then it says she runs to her classroom. Well, running means you're increasing speed. So right here, my line is going up, which means her speed is increasing. So this one is our graph. When we look at just looking at the third one, using our variables, the beginning, if she starts here, if my y-axis is speed, this means in the beginning she's speeding up, which in the beginning it was a steady pace.